Hello, I'm Dr. Robert Clifford, the Industrial Business Unit Manager of Shimadzu Scientific Instruments. Today's topic is complying with Stage 1 and Stage 2 disinfectant byproduct rules, using TOC to measure natural organic matter in source water. Also during this presentation, I will discuss trihalomethanes, THMs, and haloacetic acids, the HAA5, since they are tied so closely to the TOC parameters. Before beginning the discussion on disinfectant byproducts, I would like to give you a quick overview of the TOC terms. For TOC, there are only three things to remember. First, oxidation, or how to break down the carbon-based material. Second, how to detect the material broken down. And third, is a laboratory or online instrument required? During oxidation, the molecule is broken down into CO2 and water. The most common oxidation methods are combustion and wet chemical. The wet chemical methods include UV-Vis, heated persulfate, and UV heated persulfate. The common detectors are NDIR, or non-dispersive infrared detector, and conductivity. Combustion oxidation burns everything up by placing the samples at 680 degrees Celsius with a platinum catalyst to lower the activation energy, which converts all molecules to CO2 and water. It is the most effective oxidation method on the market. Standard Methods 5310 states it can be used for high or low levels, for refractory or hard to oxidize compounds, for high levels of suspended solids, and for high salt applications. Wet chemical techniques eat away at the outside of compounds using anywhere from 1 to 3 oxidation sources such as UV light, heat, and persulfate. Wet chemical is more sensitive than combustion oxidation, but for the drinking water community, that is not required since combustion techniques can measure down to 10 ppb, whereas wet chemical are in the sub-ppb level. The graph shows an example of a measured compound with heated persulfate in 3, UV persulfate in 2, and UV heated persulfate in 1 on the Shimadzu TOC-VW. The heated UV persulfate had the fastest oxidation method, since as one customer put it, it was like hitting it with 3 hammers instead of 2. This was published in American News, June 2002. Every detector has advantages and disadvantages. For NDIR, the advantages are it is very stable and not subjective to interferences. The disadvantage is it requires air, but house air will do. Membrane conductivity advantage is it requires no gas. The disadvantages are longer analysis time, expensive replacement modules, and interferences. Types of carbon. TC is total carbon, shown in green. Also, TOC is a combination of total organic carbon, TOC, shown in dark blue, plus inorganic carbon, IC, shown in yellow. TOC can be further broken down into non-purgeable organic carbon, NPOC, plus purgeable organic carbon, POC. If POC is assumed to be 0, then NPOC equals TOC. The advantage of this is there is only one measurement to be made. NPOC can be broken down further into dissolved organic carbon, DOC, and particulated or suspended organic carbon. Do you need an online unit or a laboratory unit? So the question is, do you want to bring the instrument to the sample or the sample to the instrument? The online units can sample up to 6 streams, while laboratory units can hold up to 93 sample vials. Online modules can sample every 3 to 4 minutes for optimization of chemical use, which will be discussed later. And some models can provide nutrient analysis for total nitrogen, TN, and total phosphorus, TP, as well as TOC. The secret to online systems is the sampling. If water is not sampled properly, the results will be poor. Shown here is a diagram of a sample thief. Sample inlet as the top left-hand corner. The sample flows back out of the system to the stream directly below that. The sample thief arm on the right-hand side moves under the sample stream and steals some sample for about 5 seconds. Below that, the sample then comes in contact with the 50 mesh rotating screen to remove the very large particles. The smaller particles in liquid are then sent down to the homogenizer to grind up the small particles. Below that, the sample is sent to the TOC via the online sample. The sample is then drained and rinsed from the top and bottom before the next sample is being prepared. From the sample thief, the sample enters the 8-port valve via the online sample near the bottom left corner. The 8-port valve can add standard acid dilution before injecting into the combustion tube. Also, I need to point out two features which were used in the sample data later in this presentation. On the syringe, you can make a multi-point calibration curve from a single high standard, and also the second is the IC removal can occur in the syringe, which can reduce sparge time by a factor of 5 compared to that of a 40 ml vial. Now let's go to the disinfectant byproduct rule. Stage 1 of the disinfectant byproduct rule was issued in 1998, while Stage 2 went into effect in 2006. The purpose of the disinfectant byproduct rule was to improve public safety by limiting the exposure of disinfectant byproducts. The rules apply to public water systems such as community water systems using disinfectants other than UV, non-transient, non-community water systems using disinfectants other than UV, and transient non-community water systems using chlorine dioxide. TOC measurements will be an indicator of natural organic material, also called NOM. NOM is from organisms that were once alive and have decayed. These organisms could have been human, animal, plant, or microorganism. To kill microorganisms such as bacteria and viruses, chlorine is added to the water samples. Not only can chlorine be used, but other forms of chlorine compounds can be used, such as chlorine dioxide and chloroamines. While these chlorinated compounds are very effective at killing bacteria and viruses, they will not kill the pathogen Cryptosporidium. The untreated water source contains many pathogens other than Cryptosporidium, such as viruses, coliform, E. coli. The source water from lakes and rivers are sent to a water treatment plant. The water is treated with chlorinated products, and the products produced are disinfectant byproducts such as trihalomethanes, haloacetic acids, bromate, and chlorite. The treated water is sent to distribution systems for consumption. Because these halogenated compounds are so tied to the NOM and TOC, there will be a brief discussion on this. Here are a few bacteria names by shape and disease. Some of the bacteria are waterborne types, others are not, but I found it interesting. The shape is in the naming. For in the top left-hand corner is the term cocca, or ball shape for Streptococcus faecalis, which is an example of a waterborne bacteria. The top right-hand disease uses bacillus, or rod-shaped, for E. coli. The bottom right-hand corner is fibrous, or curved rod, for cholera. Finally, the bottom left-hand corner is spirally, or spiral-shaped. Viruses only have one characteristic in life, and that is to reproduce. On the left is the virus pathway, otherwise known as the lytic cycle. In Figure A, there is a host cell where the virus attaches to it, as shown in B. The virus's nucleic acid is injected into the host cell, as shown in C. It begins replication and assembly process in D and E. Finally, the host cell bursts in F, releasing the newly formed virus, and the process is repeated. Viruses can occur in DNA and RNA. DNA cannot mutate, however, RNA viruses can mutate. An example of an RNA virus is hepatitis A, which can spread by the fecal-oral route, where persons ingesting contaminated food or water become infected, which is seen in countries with poor hygiene standards. So as stated, chlorine can eliminate problems of bacteria and viruses, but the problem is it can create cancer-causing disinfectant byproducts. The discussion will focus most on trihalomethanes, or THMs, and haloacetic acids, HAAs. The others are bromate from ozone treatment plants and chlorite from chlorine dioxide plants. So, what are the risks? The World Health Organization has stated that the risk of death from pathogens is at least 100 to 1,000 times greater than the risk of cancer from disinfectant byproducts. And the risk of illness from pathogens is at least 10,000 to 1 million times greater than the risk of cancer from disinfectant byproducts. In addition to chlorine, potassium permanganate can be used upstream or before chlorination for reduction of iron and manganese. Note the ions of iron and manganese in solution in red as the +2 state oxidation are converted to the solids as shown in blue, which are easily removed. Potassium permanganate can also help reduce bad taste and bad odors. The chemicals can also be used to help control nuisance organisms such as Asiatic clams and zebra mussels. In a secondary role, potassium permanganate may be useful in controlling the formation of THMs and other disinfectant byproducts by oxidizing the precursors and reducing the demand for other disinfectants such as chlorine. There are 4 THMs and they all have a similar structure. For the top diagram of chloroform, or trichloromethane, the center atom is carbon, surrounded by 3 green ions of chloride and a white atom of hydrogen. For the second compound, simply change one green chloride ion for a red bromide ion to get bromo-dichloromethane compound. The trend continues until all chloride ions are replaced with bromide ions. The maximum contamination level, or MCL, for all 4 compounds is 80 ppb. All 4 compounds together is called the TTHM, or total trihalomethanes. The chromatogram shown here is for 4 THMs analyzed on the Shimatsu GCMS with purge and trap accessory. The IS peak is the internal standard used as a reference. Analysis time is about 8 minutes. The table here shows the 5 haloacetic acids of interest, referred to as the HAA5. The top compound is monochloroacetic acid, which has 1 chloride ion in green. Add a second green chloride ion gives dichloroacetic acid, and the third green chloride ion gives trichloroacetic acid. The substitution of the blue bromide ion for a green chloride ion results in the 4th compound. The 5th compound is another bromide ion for chloride ion. The MCL for all 5 compounds is 60 ppb, analyzed by an EPA method 552.3, which is a liquid extraction, and analyzed by a GC with an ECD detector. NOM is mainly humic acid and fulvic acid. Humic acids are hydrophobic or water-hating, while fulvic acid is hydrophilic or water-loving. Thus, this affects the coagulation process, as humic acids are easy to coagulate and fulvic acids are hard to coagulate. To measure the NOM before and after the coagulation process, the surrogate parameters of TOC, DOC, and SUVA are used. TOC, or total organic carbon, the primary measurement parameter, will be discussed in more detail later. DOC is dissolved organic carbon, is simply passing the water sample through a 0.45 micron filter and measured by TOC. SUVA surrogate is a secondary test in which the ratio of UV absorption to DOC is measured. UV absorption can be measured with an inexpensive spectrophotometer such as a Shimatsu UV 1800 or UV Mini. The higher the SUVA number, the easier the water is to treat with coagulants. TOC testing procedure involves 1, 2, or possible 3 steps. Step 1 involves reducing TOC by specific percentages based on source water TOC and the alkalinity. If those percentage TOC reduction levels cannot be achieved, then a step 2 jar test is performed in which a new removal rate is established. Some waters are not amenable to effective removal of TOC, so there are alternative compliance criteria, or ACC. Stage 2 of the disinfectant byproduct rule states for measuring TOC or DOC, one can use either EPA method 415.3 or standard methods 5310B, C, or D. The method does not require any performance evaluation or PEs that are required with THMs and HAA5s. TOC and alkalinity sample sets are required every 30 days. This requires 3 pieces of data: source water TOC, source water alkalinity, and treated water TOC. Examples of how the table works is if the source water has a TOC concentration of 3 ppm, which is between the 2 and 4 ppm, and the alkalinity is 40 ppm, which fits in the 0 to 60 range, then the TOC source water must be reduced by 35%. Also notice if the source water is below 2 ppm, there is no treatment necessary. If the ratio of the actual removal to the required removal is less than 1, Then the jar test is performed by way of step 2. Coagulant is added in 10 ppm increments of alum or equivalent salt until target pH is reached based on the alkalinity. The jar test is a bench scale simulation of full scale coagulation, flocculation, and sedimentation of a water treatment process. The point of diminishing returns, or PODR, is when adding 10 ppm alum results in a TOC rate of less than 0.3 ppm in reduction. For example, in the jar test, column 1 is the jar number, column 2 is the alum added, column 3 is the treated TOC, and column 4 is the reduction in TOC. Notice in jar 5 at 40 ppm of alum added, the TOC removal was only 0.2 ppm, which is less than the 0.3 ppm reduction. This is the PODR, so the new removal rate is calculated as 1 minus the ratio of TOC removal divided by TOC initial multiplied by 100 to give percentage. Notice the value is 25%. The step 2 removal rate must be approved by the state. The graph shows an example of water not amenable to treatment when adding alum, since the treated water TOC concentration is not changing. Thus, then there is an alternative compliance criteria as the next step. The alternative compliance criteria, or ACC method, is for waters which are less amenable to TOC removal. The criteria recognizes the low potential of certain waters to produce disinfectant byproducts such as THMs and HAA5s. The alternative compliance criteria has 8 exceptions of why the water need not be treated. Items 1 and 2 are if the TOC is below 2 ppm for raw and treated water, which we saw earlier. Items 3 and 4 are related to THMs and HAA5s. Item 5 and 6 are related to SUVA, which is the UV to DOC ratio discussed earlier, if the value is less than 2 liters per milligram per meter. And items 7 and 8 are related to the alkalinity. Qualifications for reduced monitoring. THMs and HAA5s can be on reduced monitoring if 3 criteria are met at each location. THMs is less than 0.040 ppm, HAA5s is less than 0.030 ppm, and TOC is less than 4 ppm at each location. Then monitor can occur every 90 days. To remain on reduced monitoring, THMs must be less than 0.060 ppm, HAA5s less than 0.045 ppm, and TOC less than 4 ppm. However, monitoring will increase again if the THMs is above 0.080 ppm and the HA5s are greater than 0.060 ppm. If TOC levels are high, then consideration of blending water to lower the TOC levels and comply with the THMs and HA5s are acceptable. For example, groundwater has lower levels of TOC than surface water. The analytical methods for TOC utilize EPA 415.3 and standard methods 5310B for combustion and 5310C for UV or heated persulfate. DOC is the same methods as TOC, but the samples are run through a 0.45 micron filter. For UV, the measurement is at 254 nanometer absorption, and for SUVA or specific UV absorption, which is UV divided by DOC. An example of the application note on EPA 415.3 can be obtained from the link at the bottom of the slide. The title is EPA Method 415.3 Determination of TOC in Source Water and Drinking Water. The first requirement is to create a calibration curve with at least 5 points including the blank. The calibration curve here was performed on the Shimatsu TOC LCPH. The curve consists of 7 standards including the blank to ensure linearity. The standards were 0, 0.3, 0.5, 1, 2, 5, and 10 ppm, created using a single high 10 ppm standard. According to the method of minimum coefficient of determination known as R squared, should be greater than or equal to 0.993, but is recommended to have above 0.9995 for best results. The R squared here was 0.9996, which is considered under the best results category. The method requires inorganic carbon or IC removal efficiency tests. A solution of 9 different salts is made up to simulate that of a waste treatment facility. The final concentration of inorganic carbon is 102.5 ppm. There are 2 IC removal efficiency studies shown here. The top table is from the method itself using the 40 ml vial to sparge. After 10 minutes, the IC value is 0.61 ppm, which is still above the 0.35 ppm required for completion of the test. The bottom IC removal study was done on the Shimadzu TOCL CPH, and it can be seen that after 2 minutes the IC is below the 0.35 ppm value at 0.30 ppm. Of important note, the syringe sparging method is 5 times faster than the vial sparging method. It does not matter if this is a Shimadzu online or lab unit, the results of the syringe sparge will be the same. The detection limit study requires 7 repetitions be analyzed each day for 3 days. The Shimadzu TOCL CPH used 2 different catalysts, and the results were 0.0697 ppm and 0.0175 ppm for regular sensitivity catalysts and high sensitivity catalysts, respectively, which both were well below the required 0.35 ppm limit. The injection volumes were only 50 and 81 microliters. Those values could be increased to 300 and 2,000 microliters for improved detection limits if needed. In method 415.3, there are some QA testing calculations. The equation 1 is a recovery of the QCS and CCC. QCS is the quality control standard, and CCC is the continuing calibration check. For example, the percent recovery is the measured value divided by the true value times 100. On the next slide, you'll see those results. Here's an example where the measured value was 4.92 ppm, the true value was 5, so the result was 98.4%. Equation 2 is the relative percent difference between duplicate samples. So the RPD is field duplicate 1 minus field duplicate 2 divided by field duplicate 1 plus field duplicate 2 divided by 2. In the example on the next slide, you'll see the results were 1.15 ppm, or rather 1.51 ppm minus 1.59 ppm divided by 1.51 ppm plus 1.59 ppm divided by 2, and the relative percent difference was 5.16 ppm. Equation 3 is a percent spike recovery. Percent spike recovery is A minus B divided by C times 100. A is the measured concentration in the fortified samples, or the spike. B is the measured concentration in the unfortified sample, or the original sample, and C is the fortified concentration. So we measured 6.23 ppm in the spike sample minus 1.51 ppm in the original sample divided by the spike concentration of 5 ppm gave a recovery of 94.4%. Shown here are the results of the QA tests for drinking water. The QCS is analyzing the 5 ppm standard, and the results reading back 4.92, which is a recovery of 98.4%, well within the TV or true value results of plus or minus 20%. The CCC was analyzed on the lowest standard of 0.3 ppm, which should be the most difficult, and the recovery was 83.3% within the true value of plus or minus 50%. Also notice at the bottom of the slide is the calculation for minimum report level, MRL, of 0.29 ppm, which is similar to the lowest standard. The Columbia and the Columbia FD are duplicate samples, and the result was within 5.16% difference, which is less than the 20% RPD that's required. And the spike of the Columbia is 1.1 or 1.51, and the sample spike was 5 ppm, which resulted in a 6.23 ppm for a spike recovery of 94.4%, well within the plus or minus 30% TV value. Similar QA information is available for the source water. For example, the QC results for the 0.3 ppm were 106.7 within the 20% FTV value. The Centennial FD, or field duplicate, was 3.15, relative percent difference within the 20% RPD. The little Patuxent spike with the 5 ppm where results at 95.8%, well within the 30% true value. And the continued calibration picked a midpoint this time, and you can see how close it is at 101.4% recovery. Here are some of the links I used in this presentation. As I mentioned in the beginning talk, also at the bottom of some of the slides are other links. In conclusion, I think we've learned to comply with the disinfectant byproduct rule 1 and 2, the importance of tier C items such as reliability, maintenance, automation, selection between online and laboratory units, required related parameters such as THMs and HAA5s, other optional parameters needed like TN, total nitrogen, and TP, total phosphorus, how to optimize the treatment to save money, TOC testing procedure, alternative steps and alternative compliance criteria, and TOC method EPA 415.3. Thank you for your time, and if you have any questions, please feel free to contact me. Have a good day. Bye-bye.